2017 Colloquium Fest. So there are a total of 16 talks going on today. There are 3 this morning in 3 parallel sessions, plus minus 1, I think, plus 4 more sessions this afternoon with 2 talks each. Each talk is going to be about half an hour plus 5 or so minutes for questions. There'll be a break about 10 minutes in between. Students can go and sign up for credit on the table outside. There's like lots of iPads and laptops and all that fun stuff to log into. And then also from, I guess, 11:40 until 1, there will be a pizza lunch up in the library for all of the students. And yeah, in terms of upcoming other events in the math department, besides the other 15 talks today, there is also a colloquium tomorrow on the central values of L functions. That's at 1 p.m. in the usual Bronfman 106. Without further ado, let us go ahead and get started. So our first speaker of the day is Ben Solis-Cohen, who will be telling us about Ramsey theory. Let's welcome Ben.
Today we're going to be talking about Ramsey theory, and the idea of Ramsey theory, summed up by Theodore Motzkin, is complete disorder is impossible. So specifically, given a large enough structure, we can guarantee the existence of certain substructures. So let's explore the idea further through the following proposition. Given a group of 6 people guaranteed 3 mutual friends or 3 mutual strangers. So to demonstrate this, I'm going to look at you 6 people. So Mihai, Ellie, Gabby, Steven, and Marcus. How do you guys know each other? Okay, it looks like we have 3 mutual friends. They all know each other. If there were 3 people, none of whom knew each other, that would be 3 mutual strangers. So, in this example, the proposition is satisfied, but how do we prove something like this? Well, we can state an equivalent proposition in terms of some of the graph terminology on the board. But first, let's explain some of it. So, a graph is a collection of vertices connected by edges. Here's an example of a graph. Actually, all these pictures are graphs. A vertex is one of these dots, and connecting them are these lines, and they're called edges. We're going to be dealing with simple undirected graphs. What that means is there's no loops, and there's no multiple edges between 2 vertices, and there's no directed edges. So edges don't have directions. So it looks more like that, or like this one. Okay, so the order of a graph is the number of vertices in the graph. So the order of this graph, for example, is 4. The degree of a vertex is the number of incident edges. So the degree of this vertex here is 1. The degree of that vertex is 3. A complete graph is a graph where all vertices are connected to all other vertices. Here's an example of a complete graph, because everything's connected. Kn is just how we denote a complete graph of order n, so with n vertices. So this graph here is called K6. We're going to be using complete graphs a lot. A subgraph, h of g, is just obtained by deleting edges and vertices, so it's just like a part of a graph. A clique is a complete subgraph, and a k-clique is a clique of order k. So, for example, this right here is a 3-clique of this graph, because there's 3 vertices and it's a complete graph. So, for example, so a 3-clique is like a triangle. The last term is an m coloring, which is an assignment to each edge of a graph with one of m colors. We're going to be dealing with 2 colorings mostly, and this right here is a 2 coloring of k6. Because every edge is assigned a color, and it's either red or blue, 2 colors. So right here is actually a good example of what the equivalent proposition we're going to state. And the way we're going to prove this with graph theory is that each vertex represents a person, and the edges between them represent the relationships between the people. Every person has a relationship with every other person, so it's a complete graph. And basically we're going to say that a red edge represents a stranger relationship, so these 2 are strangers, while these 2 are friends because there's a blue edge. So, restating the proposition, we can say any 2 coloring of K6 contains a red or blue inclusive 3 cliques. Okay, so now we can prove it. So begin, we're going to select an arbitrary vertex V. And we can put the 5 other vertices in K6 here. Since it's a complete graph, we're going to fill in these edges. There's edges between all vertices. And we need to color every edge either red or blue. So by the pigeonhole principle, we're going to be guaranteed at least 3 red edges from V to these vertices. We'll call these vertices S, these 5 vertices. We're going to be guaranteed, we'll say, at least 3 red or 3 blue edges from V to S. Okay, so now, without loss of generality, the proof actually goes the same if you say that there's 3 red or 3 blue. We're going to assume that there's 3 red going from V to S, and we'll draw those here. So we're guaranteed this little structure, in this case, actually in general, in every single 2 coloring of K6. So how does this help us? Well, we can, first we'll call these T, which is a subset of S, those 3 vertices, and we can break into 2 cases. Case 1 is that there's at least 1 red edge in T. Well, the reason that that helps us is because you can see that if there's at least 1 red edge here, then we're guaranteed a red triangle. And so case 1 leads to a red K3, complete graph on 3 vertices. Case 2, since we already covered the case where there's at least 1 red edge in T, case 2 is just, we're just left with cases where there's no red edge in T. And the reason, and that's helpful because we're doing a 2 coloring. So since we've eliminated all red edges, the only edges that can be left in T are blue edges. And so what we're left with is a blue triangle. So case 2 always yields a blue K3. And that actually completes the proof. Because in any 2 coloring of K6, we're guaranteed either a red K3 or a blue K3. Okay, so, but is this the best we can do? Can we guarantee 3 mutual friends or 3 mutual strangers with 5 people? And we can also look at that using a graph. So let's look at K5 now. And we can look at a 2 coloring of K5 where there's no monochromatic 3-click. So here, if you look at it closely, there's no red triangle, there's no blue triangle. So with 5 people, we're not guaranteed 3 mutual friends or 3 mutual strangers. And thus we found that 6 is the minimum number of people, such that we're guaranteed 3 mutual friends or 3 mutual strangers. And that motivates the following definition of Ramsey numbers. So definition of a Ramsey number for integers S and T, S and T both greater than or equal to 2. The Ramsey number, we denote Ramsey numbers called by saying RST, is the minimum number n such that any 2 coloring of Kn contains a red S-click or a blue T-click. Okay, so what we've actually found here is that R33 equals 6. How do we do that? Well, here we showed that we don't need any more than 6 vertices to guarantee on the on any 2 coloring of the complete graph on those vertices, either a red 3-click or a blue 3-click. So R33 is less or equal to 6. Here we proved that on K5, we don't have a red 3-click, we don't have a blue 3-click, and thus we can find coloring on K4, on K3, on K2, all the way down to K1, such that there's no 3-click, there's no monochromatic 3-click. So we've shown this, and together they imply that R33 equals 6. So that's how we can proceed with more proofs of Ramsey numbers. Let's find the simplest one, R22. Because by the definition they have to be, they have to be greater than or equal to 2. So R22, how do we find that? Well, let's look at K1, very simple graph. It's just one vertex. Can we find a coloring where there's either a red or a blue edge always? Because a K2 is actually just an edge. It's K2. Well, actually, there's no edges here, so we can never find. That's like there's always a counterexample. What if we add another vertex? Well, this edge here is always colored either red or blue. So there's always a red or a blue edge here. So we don't need any more than two vertices to guarantee always either a red edge or a blue edge. And thus we conclude that R22 equals 2. Okay, one more, R23. Well, we can look at two vertices again, and this time we color this edge blue. So there's no red edge, there's just a blue edge, and there's no blue K3. So here we've actually shown that R23 is strictly greater than 2, and just by adding another vertex, we can look at a coloring of K3, and we can sort of proceed like we did at this proof. We assume that there's one red edge, and then great, we're guaranteed a red edge. But if there's no red edges, then all edges are blue. And so in that case, we're guaranteed a blue K3. So we don't need any more than 3 vertices to guarantee one of these two structures. And thus, R23 equals 3. Okay, so what about R2N? Does anyone have a guess for what R2N is?
Maybe N.
Yeah, R2N is N, because, I mean, you can sort of see it counting up, but let's see if we can prove it. So let's look at K sub N minus 1, and we're going to color every edge in Kn minus 1 blue. Well, there's no red edge, because every edge is blue, and there's no K complete blue Kn, because there's only N minus 1 vertices, so this must be strictly greater than N minus 1. Also, then if we add a vertex and we look at Kn, we can just proceed just like we did in this case, where we assume there's one red edge, and then we're good. So we only have to worry about colorings where there's no red edges, and that means the coloring that's just one of those, where all edges are blue. And that's exactly what we're looking for. That's the other structure we can find. And so we've shown that R2n is less than or equal to N, which shows R2n equals N. All right, great. So we found a bunch of Ramsey numbers. Now, it's clear that important in these proofs of Ramsey numbers are finding upper and lower bounds. We sort of narrow in on the Ramsey number and then we conclude equality. So let's try to find a general lower bound for the Ramsey numbers. And specifically we're going to be looking at a bound of the Ramsey numbers of the form RKK. So here's the theorem that we're going to prove. So this is the theorem. It's that for k greater or equal to 2, r k k greater or equal to 2 to the k over 2. So what does that mean? Let's just review what RKK is. That is the minimum number of vertices, such that on any two coloring of the complete graph on those vertices, we're guaranteed either a red or a blue k-click. So what is this statement saying? That's saying that we're going to need more than 2 to the k over 2 vertices to possibly guarantee either a red or a blue k-click. So first, a couple of base cases. R22 equals 2 and R33 equals 3. 6 we proved over there. So now we're just going to prove this theorem for k greater than or equal to 2. And the way that we're going to prove it is there's this thing called the probabilistic method of proof. And the way that works is if you can prove that a certain structure occurs with positive probability, then you conclude that that structure must exist, because it has to be present in the sample space for it to have positive probability. So what structures are we looking for? Well, first we're going to randomly color a Kn so we're going to say for n be strictly less than 2 to the k over 2. So we're looking at a smaller graph than 2 to the k over 2 vertices. And we're going to randomly color it, color the complete graph on n vertices. And so what we're going to show is that if we have a small graph, if n is strictly less than 2 to the k over 2, then we might not have a red or a blue k-click. And so we're going to show the structure existing by the probabilistic method of proof. The structure we're going to show is a two coloring of Kn, where n is small, where there's neither a red nor a blue Kn. So how does that work? Well, how are we going to randomly two color this graph? Well, we're going to color each edge red or blue, each with probability 1/2. So that means we flip a coin every time we want to color an edge. Flip a coin for the first edge. If it comes up heads, color it red. If it comes up tails, color it blue. Do the same for the second edge. Flip a coin again. So we color all edges independently with probability 1/2. So then we're looking for these k-clicks. So let's define A as a k-click. Any k-click in Kn. And let's say that AR is the event that A is red. So what do I mean by A is red? I just mean every edge in A is colored red. What's the probability of the event AR? Well, the probability that we color the first edge red is 1/2. Probability that we color the second edge red is 1/2. Probability that we color both edges red simultaneously is 1/2 times 1/2. So it's a 4. So really what it is 1/2 times the number of edges in the k-click A. So how many edges are there in a k-click? Well, every two vertices, order doesn't matter, uniquely identifies an edge. So how many ways did it pick 2 vertices out of k vertices? Just k choose 2. So that's how many edges there are in a k-click. So then we found the probability of some arbitrary k-click being colored all red is 1/2 to the k choose 2. How does that help us? We're not looking for just the probability of some arbitrary k-click. We're looking for the probability of at least one red k-click occurring. So let's call that PR, and let's try to define it in terms of probability of AR. So PR is the probability of at least one red k-click occurring in this random 2 coloring, and we can rewrite it as the probability of the union over all possible k-clicks that at least one of those k-clicks is colored red. And we showed by lemma 1, Boole's inequality, the probability of the union of some events is less than or equal to the sum of the individual probabilities. So now we have that by Boole's inequality. And we know this, and we actually also know that it's true for every single k-click. So what we can do now is we just have to figure out how many k-clicks there are, and then we can just get rid of the sum. So how many k-clicks are there in this graph? Well, sort of like we figured out how many edges there are, k vertices uniquely identify a single k-click. So how many ways did it pick k vertices and n vertices? Just n choose k. So this is n choose k times the probability of AR, which is 1/2 to the k choose 2. Okay. Great. So we're trying to make this small, this probability, because we're trying to show that there exists a 2 coloring where there's no red k-click, or blue for that matter, but we'll deal with that in a second. So how do we bound this probability? We can use lemma 2, which says n choose k plus we go to n to the k over 2 to the k minus 1. So we just apply that lemma here. Okay, so that means that this probability is less or equal to n to the k over 2 to the k minus 1 times 1/2 to the k choose 2. And we also know that n is strictly less than k over 2. So we plug that in here. 2 to the k squared over 2, so we raise it to the k over 2 to the k minus 1. And we bring down this 1/2 to the denominator. K choose 2. Okay, so now we have a bunch of 2's with exponents. Yeah, never seen.
No, I was just wondering why, is there some reason you can't just do 1 minus the probability of having all blue k-clicks?
All blue k-clicks.
Wouldn't that get you the probability of at least 1 red?
Clicks don't have to be, a click doesn't have to be all red or all blue, it could be a mix, right? So 1 minus the probability of a blue k-click isn't necessarily the probability of a red K click could be mixed. Okay, so that's 2 to the K squared over 2. We get a negative K squared over 2 from the K choose 2, and we have minus K, and we get a positive K over 2 from here, and then plus 1. So that, these cancel, and that's a negative K over 2, plus 1, and since we have that K is greater than or equal to, whoops, this is a 4, since we showed it for 2 and 3, we're just proving it for K greater than or equal to 4, and so this right here is less than or equal, since there's a negative sign, negative 2 to the negative 4 over 2 plus 1, and that is just a half. So we've shown that PR is strictly less than a half. Probability of at least one red K click is strictly less than a half, and we could have done the same proof for a blue K click. And so, because they're colored with equal probability. So the probability of a red K click is actually equal to the probability of a blue K click. So we conclude they're both at least one. Or we conclude that they're both strictly less than a half. So what is the probability that we're actually looking for? It's the probability that in the 2 coloring, we're looking for the probability that there's a 2 coloring with no red and no blue K click. And sort of like you were saying, this is equal to 1 minus the probability that there's either at least one red or one blue K click. And so let's find that. That is the probability of at least one red or at least one blue K click is less or equal to the sum of the individual probabilities by Boole's inequality again. And we know those to be strictly less than a half plus a half, which is 1. So we showed that this probability is strictly less than 1, which means that this probability is strictly greater than 0, which means that there exists a 2 coloring of Kn, where n is small, it's strictly less than 2 to the K over 2, with no red and no blue K click. And so what that means is that we can't guarantee, if n is smaller than 2 to the K over 2, we have fewer than 2 to the K over 2 vertices, we can't guarantee a red or a blue K click, and thus we're going to need more vertices. We're going to need more, at least 2 to the K over 2 vertices to guarantee one of those 2 properties. That completes the proof. How's the time?
Got about 9-10 minutes.
Oh, okay, great. So now we're just going to find one more Ramsey number. We're going to conclude with one more Ramsey number, R34. I guess where's that soon? Okay, so I don't know if any of you have a guess for what R34 is, but here's another theorem that I'll give you, that R ST is less or equal. Okay, so this can help us find a guess for R34. Well, let's plug in R34. Well, so we subtract 1, so that's R24 plus R33. And we know both of those. We figure those out at the beginning. That's 4 plus 6, which is 10. Okay, so in order to prove that R34 equals 10, here this theorem says that it's less or equal to 10. To prove that it equals 10, we have to find a graph on 9 vertices with no red and no blue no red 3 click and no blue 4 click. But I couldn't find that because actually R34 equals 9, so we're always guaranteed one of these 2. And so what we really want to prove is the proposition R34 is less or equal to 9. This graph that fell over here shows that R34 is strictly greater than 8. You can look at it later. It's pretty small. So R34 is less or equal to 9. You can just trust me that proves that R34 is greater than 8. So let's just prove this. Okay, so we're going to start sort of similarly. Notice we're not actually using this theorem because we're actually just going to directly prove that it's less than or equal to 9. But this proof here of R34 is actually very similar. It's actually, the case 1 of this proof is sort of the proof of this theorem. And you might be able to see that as I'm going. So, because we're going to sort of use these facts. Okay, so let's see, we're looking at K9, and we're seeing if we can guarantee in every 2 column of K9 either a red 3-click or a blue 4-click. So we have our 8 other vertices that I'm going to put here. There's 8 vertices here. And so since it's a complete graph, we're going to have 8 edges. Here, there's 8 edges here. And let's call this set of vertices S, these 8 vertices. And we'll say that the red edges from V to S we'll call R, and the blue edges from V to S we'll call B, and we'll say that that equals 8, because there's 8 edges here. Okay, so we're going to split into 3 cases now. Case 1, case 2, and case 3. Case 1 is that the number of red edges from V to S is greater than or equal to 4. Case 2 is that the number of blue edges is greater than or equal to 6. And case 3 will be the negation of cases 1 and 2, since we're trying to look at all possible cases. That's that R is strictly less than 4, and B is strictly less than 6. Okay, so these partition all cases. Specifically, we're saying that, so we chose this V arbitrarily. If we're, okay, we'll get to the specifics in a second. Okay. So let's deal with case 1 first. And to remind you, we're trying to guarantee either a red K3 or a blue K4. So case 1. Case 1. Oops, forgot my red chalk. Okay, so in case 1 we have our 4, we said there's at least 4 red edges going from V to S. We'll call these vertices that have red edges going to them, we'll call those T1, which is a subset of S. Well, notice there's 4 vertices here, and we proved again that, we proved at the beginning that R24 equals 4. What does that mean? That means that any 4 vertices, we're guaranteed either a red edge or a blue K4. And so, here's 4 vertices, and so on these 4 vertices, we're guaranteed either a red edge or a blue K4. Case 1 is we're guaranteed a red edge, so there's a K2 in T1. If that's the case, then sort of similar to our first proof, we have a triangle. So this step leads to a red K3, subcase 1A. Subcase 1B will be that there's a blue K3 in T1. So there's a K4. Blue K4 in T1, so right in here. But actually we don't need to do any more work because that's exactly what we're looking for. So in case 1, we're guaranteed either a red K3 or a blue K4. Great. What about in case 2? In case 2, we have our vertex V again. And we have, this time, we said in case 2 that there's 6 blue edges at least from V to S. 1, 2, 3, 4, 5, 6. Okay. And we'll call these vertices here, we'll call these T2 subset of S. So they could be different ones from here. And so, again, we proved that R33 equals 6. Well, here's 6 vertices again. So in subcase 2A, we're guaranteed either a red K3 in T2, in which case we're done, because that's what we're looking for, a red K3. And in case 2B, we're guaranteed a blue K3 in T2. So blue K3 isn't exactly what we're looking for, except it's great that it's in T2, because T2 has all blue edges coming from V to T2. So actually what we're looking at is a blue K3 in T2, but together with the edges from V to T2, it actually creates a blue K4. And so in case 2B we're guaranteed a blue K4. So great. Red K3 or blue K4. So finally, last case of the day is case 3, which is a little bit tricky. So case 3, this is sort of what made us go from 10 to 9, because these 2 cases are sort of like the concrete proof of that theorem, but this case is what brings us down from 10 to 9. This is like extra work. So case 3 is that R is so we said that R is strictly less than 4 and B is strictly less than 6. If you combine it with this thing that we said at the beginning, that R plus B equals 8 because there's 8 edges from B to S, then actually case 3, the only way those two things can be satisfied is if R equals 3 and B equals 5. That's the only way to satisfy R strictly less than 4, B strictly less than 6, and R plus B equals 8. And the thing is that if case 1 or case 2 is true for any vertex, then we're done. Because we just chose one vertex and we showed if either of these are the case for any one vertex, then we're done. So we only need to worry about case 3 if it's true for all vertices. So in case 3, this is actually true for all vertices. And so how does that help us? Well, we're going to be using lemma 3, that in any simple undirected graph, there's an even number of vertices of odd degree. So it looks like we're fine here because there's 8 edges coming out of each vertex, except if you look at the blue subgraph, so that means deleting all red edges. So if we're delete all red edges, we're just going to look at the subgraph of this graph that's blue. And notice that for every vertex, each vertex has 5 edges coming out of it that are blue. So we have 9 vertices in K9. In this blue subgraph, there's 9 vertices, and each of them have degree 5. And I couldn't draw this graph for you because it doesn't actually exist. Because there are 9 vertices, each of degree 5, which is an odd number of vertices, and each vertex has odd degree. And that says that there must be an even number of vertices of odd degree. So by lemma 3, case 3 leads to a contradiction, and thus we're stuck in cases 1 and 2, in which we're guaranteed either a red K3 or a blue K4. I think maybe some of you, does this make sense?
Why do you need to use the blue, the 5?
Right. Oh, you could use the red.
Yeah,
Good. Yeah, you could use either one. Yeah, that's right. But yeah, you just have to delete one of them, or just look at one of them. Okay, so great. So now we've proven that R34 is less or equal to 9, and by that graph that's folded over, you can look over later. It's greater than 8. So R34 equals 9. Great. Okay, so that's the last proof of the day. I just want to conclude with a quote by Paul Erdos. He was trying to say that these numbers are really difficult to calculate. This chart here that I'll try to show you is all the Ramsey numbers that we actually know. They're symmetrical along the diagonal because you can always swap the colors, so RMN equals RNM. And the green ones, well, my printer sort of did a bad job coloring it green, but the single numbers are the numbers we know, and the ranges are sort of bound to the numbers we don't know. There's like 9 numbers. If you delete half of them by symmetry, there's like 9 numbers we know, and we found 4 today. Delete the trivial ones also, like R2M. So these numbers are really hard to calculate, and Erdos said that if an alien race came and demanded that we give them R55 or they would destroy our planet, we could probably have the whole math world come together and find R55 and appease the aliens. But if they ask for R66, then we should just mount our best defense because we would never find it. So that concludes my talk. Thank you very much.
Any quick questions for Ben?
Oh, yeah.
Yeah?
So you showed us a lower bound here for RKK. Is there a nice upper bound, maybe derived from that inequality?
Oh, yeah, that is a, oh.
So you say RKK is greater or equal than 2 to K over 2.
Right.
Well, not
So you
necessarily.
can't use that for RKK because, yeah, so you could just plug in RKK here. Okay. Are you saying is there a better one?
No,
than
no,
this?
no, but what would that method or any other method, what do you know a good upper bound for RKK?
So better than just plugging RKK into that upper
Or
bound.
that, but
Yeah,
it
well-
should give you a formula, no? Is there a nice formula?
Oh, yeah, so there are like many really good formulas for Ramsey numbers. I don't know one for RKK off the top of my head, but there definitely is. Like there's been a lot of work on in general upper and lower bounds for Ramsey numbers.
Do you know one that's not optimal, but for RMN?
Yeah, an upper bound?
But a formula, not a...
Oh yes, you can actually use this. You can prove by induction very quickly a formula using Pascal's triangle formula. You can actually prove by induction a nice closed form upper bound using this recurrence. Yeah, it's like n or r plus s plus t minus 2 choose like s or something. Yeah, you go with that.
Any other questions? Awesome, let's thank Ben again. And we'll get started with our next talk in 10 minutes. You can sign in for colloquium credit on the table out.
All of them. R4.